Hello, everyone. Welcome to this week's Crunch seminar. Today we have one speaker. Our speaker is Nikhila Kalia. She's currently a master's student at the University of Waterloo, pursuing a mechanical engineering. She graduated from the University of Waterloo with a bachelor's in mechanical engineering and has some previous cooperation experience at Tesla, ANSYS, and Lithium's Automotive. Nikhila, with this short introduction, the floor is yours, and you can start whenever you're ready.
Thank you so much. Hi everyone. Thank you for the introduction. My name is Nikhila, and I'm currently a student at University of Waterloo in Canada. And today my talk is going to be on the use of Kolmogorov-Arnold networks for turbulence and isotropy mapping. So just a quick outline for the entire presentation. So we're going to start with our motivation, problem statement, brief introduction to CANs, the model architecture, methodology, and then going to the test cases and results, and then concluding the work. So the first question that arises is, why is turbulence modeling difficult? Why do we need machine learning? So turbulence modeling is inherently something that's chaotic, multi-scale, and nonlinear. In CFD, you have direct numerical simulation, which is DNS. So it can resolve all the scales of turbulence up to the the Taylor microscales, the Kolmogorov microscales, and then this is super expensive and takes a lot of time, and it is not really feasible for high Reynolds number flow. Then you have the LES, which is the large eddy simulation. It can still resolve large scales, but requires super fine grids near the walls. But then when we come to the industrial setting, we need to sort of prioritize computational efficiency. So simplified models like RANS, which is the Reynolds average Navier-Stokes, is used, but this obviously comes at a cost of accuracy and generalizability. So why is RANS modeling still a challenge? So as I mentioned, Reynolds average Navier-Stokes RANS models they use empirical closures for the Reynolds stress tensor, which I'll just get into in the next slide. So these closures, they often fail in flows where you have strong anisotropy or like separation, reattachment, or secondary flows and separation zones. So in flows or like test cases, as we'll see as we go through the presentation, RANS predictions can, miss out on a lot of important things, which you would usually see in DNS or LES. So if I look at the U momentum equation for RANS, I have this tau ij term on the right. So this is the Reynolds stress tensor, and this is the closure problem. So this is the unclosed term in this equation. So this can be decomposed into the isotropic and the anisotropic component. So the anisotropic component, Aij, is the main focus of the talk today. So traditional closure models, especially the two equation models in RANS, they use the Boussinesq approximation to model to close this term. So this assumes isotropy and linearity. So it's not a accurate assumption. So just going over some common two equation turbulence models that are commonly used in the industry are the K epsilon model, K omega, and then you have the K omega SST, which is the shear stress transport. So we have a transport equation for the TKE, or the turbulent kinetic energy, and then usually you have a second variable, which is either epsilon, which is the turbulent dissipation rate, or omega, which is the specific dissipation rate. So the K epsilon model is widely used, especially in free shear flows, but the near wall accuracy is limited. So to sort of get around that, you use dampening corrections, and then there's some correctors within the models that people use. K omega, it's sensitive to free stream boundary conditions, but it has really good behavior near the wall regions. And then K omega SST is sort of combining the two models, and then you're combining the advantages of both K epsilon and K omega. So K epsilon in the free stream region, and then K omega in the near wall region. So this is probably one of the more common model that people would use for adverse pressure gradients and separated flows. So coming back to the closure problem, so Pope proposed this nonlinear framework where Aij can be broken into this complex mathematical function. So this is Tij is essentially a tensor basis function that's constructed using the normalized strain rate and the rotation rate tensors. And the Gn over here are the scalar coefficients that our goal is to learn via machine learning. So the idea of using Pope's expansion is so to make sure that we are still following Galilean invariance and rotational invariance. So essentially, even if our reference frame moves, our coordinate system rotates, we're still, it does not change the values that we receive by solving this expansion. So if I just sort of show the 10 tensor basis terms, and this kind of puts into perspective how tricky it would get after solving just Tij1. And then as you go down, it becomes more and more complex. So this entire tensor basis is derived from the normalized strain rate and rotation rate tensors, which are the Sij and the Rij tensors. So the problem statement that we sort of came up with is predicting the anisotropic Reynolds stress tensor, Aij, from Rand's resolved quantities. So the approach that we implemented was using machine learning, that is CANs in this particular scenario, to learn the mapping from the scalar invariance to the weights. So we're essentially predicting GNs, and then we're going to embed the learned Aij back into the Rand's momentum equation using OpenFOAM. So in this study and this presentation, we're going to assess the model performance, and our benchmark is going to be the modified TBNN, which is a word that I'll use quite frequently, which is the tensor basis neural network. This is based on MLP, so this is based on the multilayer perceptron. The work that we would be comparing this to is that would be with CANs, would be called TB-CAN. So that's tensor basis Kolmogorov-Arnold network. And we would be benchmarking this against DNS, which is our ground truth, and then also the modified TBNN, just to see how CANs sort of compare to MLPs. So just a brief introduction about what CANs are. So this is a novel neural network that was recently brought to light by Liu's paper, which is based on the Kolmogorov-Arnold representation theorem. And I believe the theorem itself has been around since 1956 or 57. So unlike MLPs, where we have a fixed weight and the nonlinearity is applied at the node, the CANs place the learnable nonlinear functions on each edge. So this figure here is adapted from Liu's paper, where it's sort of a visual understanding of how the learnable activation functions are on the edges for CAN, and then the sum operation on nodes. So why do we want to use CANs essentially? So this work, as I just want to explain, is a drop-in replacement for MLPs. So while reading the original paper presented by Liu, they were only dealing with toy problems and not with super complex turbulence problems, I guess. So the goal here is to evaluate whether spline-based CANs can actually match or outperform MLPs on a very highly nonlinear and physics-informed task. So the Rand's anisotropy closure problem is a challenging benchmark because of its complexity in itself, and also the high dimensional vector space that we would be working in. And again, I just want to sort of reiterate that this study is like an initial testbed for CANs in scientific machine learning. And the whole idea of doing this was testing the claim whether, are these better than MLPs or comparable. So learning the anisotropic stress, like just to break down the framework into a few slides. So the objective is to essentially learn the scalar weights Gn in this tensor expansion. So the input features that we would be using for our study are the scalar invariants that are computed from normalized Sij, Rij, and the omega and the k values. So this is originally shown from Wu's paper and McConkey's. So Sij Rij is something that has been used in the past, but it only gives you 5 input features, which are pretty sparse, especially in a 2D flow where they come down to 2. But then in our input domain, we're also using, we're also using input features that are derived from the specific dissipation rate and the turbulent kinetic energy. So the output is the anisotropy tensor, the Aij, which is matched to the DNS results. So the models that, as I mentioned before, we would be talking about constantly is the modified TBNN, which is the tensor basis neural network, which would be using MLP, and then TB-CAN, which is the tensor basis Kolmogorov-Arnold network that is using CANs. So the repositories.
Can I ask a question?
Yes.
For the input features, so that you assume that you know this at every iteration, let's say, everywhere in the domain, right? And you have to iterate between the two, right? Because Aij determines Sij.
So the input features are originally taken just from the original RANS simulation, if that makes sense.
From
so
the RANS
it's
or from the, I thought the Sij, you get it from the, actually, that's a good question. Sij, because I don't know that paper of 3 and 4 that you referenced. Can you give a little more context?
Sure. So I guess the first paper that I probably should also mention here is the Link's paper, which was the Link 2016, I believe. So that paper essentially starts using lambda 1 to lambda 5 as input features for their MLP based network that they call the TBNN. And they are taken from just the baseline RANS simulation. So it's not sort of resolved at each step.
Right. I know that paper.
Okay, yes. So and in addition to that, we also take the input features from the TKE and the specific dissipation. So we have, I think, a list of maybe 47 heuristic scalars that we come up with instead of just the 5. So it's that one is like more in depth in the paper 4 as on the references, but those input features are essentially the same that carry forwarded from both the MLP into the CANs network. So it's the same set of features.
Thank you.
Hi, I have a related question here. So as you said, the input feature is calculated based on converged RANS field, right? Converged RANS simulation, and the output is coming from the DNS. And I guess the velocity, so say the mean velocity of the RANS and the DNS are somehow different, right?
Yes.
Okay,
so
okay, got it.
The output, the GN, so we're still getting that based off of the so when our input features come out of RANS, we're still getting the GNs that are sort of based on that. But then when we get the Aij, we sort of compare it for a loss, like how different it is, taken from DNS.
Yeah, got it. But if you use the Aij you get in the RANS solver, so the input feature will be different because the velocity field will be different from the initial RANS condition. So it's somehow, so in that case, the RANS and DNS are not coupled.
Yeah, they're not related to each.
Okay.
We're not putting anything from DNS into our study. That's only there to benchmark it and like get the errors. So even the as I go forward and I explain the injection step, you'll see that even the TKE values that we use to compute Aij is something that we use another network that we call the KCNN, which I'll again get into it as we go forward. And we don't use the K values directly from DNS because I guess that's cheating.
Yeah, I got it. Thank you.
No worries. Okay, so yeah, so the two models will be the modified TBNN, which would be referring to the MLP structure, and then TBCAN, that would be referring to the CAN structure. And both the repositories for both of them are available on GitHub if anyone's interested. So just a visual representation of the training architecture. As I mentioned, we have the input layers where we have the scalar invariance. Then we have the hidden layers, which represent the CAN structure. And then we have the coefficient layer, which is GN. So at the end, when we have the tensor basis input layer, those are essentially just being multiplied to GN to produce that, the Bij tensor. So over here, you can see that we have something called the realizability informed loss, which is something I will get into it just in a few slides. And then we have the K value, which is used to go from Bij to Aij. And the error loss that we compute is using Aij theta, which is what we get from DNS. So that's just understanding how far off we are from the true values, which are DNS. So the training architecture, we just went through that. And then we have a separate architecture for injection because we want to inject the Aij field, the Aij values that we get from the training back into the U velocity fields to understand how accurate they are, right? So the train TBCAN is integrated into the RANS framework. So, well, at each iteration, when we get the scalar invariance, they're computed from the RANS flow field, and then they're passed through the TBCAN to predict the anisotropy tensor Aij. And then we reconstruct the Reynolds stress, the tau ij term. And then this stress tensor is injected back into the RANS momentum equation. So I just want to show the injection process once, and then I'll get back to the closure strategy. So we have this RANS momentum equation at the bottom, as you can see. So we have this Aij term that's being injected back into the RANS momentum, in the U momentum equation. And then we have that Kr value right between Bij and Aij. So that's the TKE value correction that we also use from RANS. So the superscript R is referring to RANS. And if I go back, so one thing you would have noticed that we use a hybrid injection strategy. And the reason we do this is for numerical stability. So the G1 term is treated implicitly. So as you can see, I've hashed out the G1 term. So that's implicit. And then the remaining terms, G2 through G10, are treated explicitly. So they're injected directly at each iteration from the TBCAN output. So the idea to deploy this strategy is so that we can increase the diagonal dominance by implicit treatment. So this is important because it helps with stable convergence, and also instability is avoided that might arise from like a fully explicit nonlinear closure. Okay, so what is KCNN? As I just mentioned, so the kinetic energy correction network is augmenting the anisotropy tensor prediction by scaling the predicted turbulent kinetic energy, so the K-pred value. So the reason there's a different network that gets the KCNN values for us is because if we just took it from DNS, that, as I mentioned, would be probably cheating, because this allows independent correction of the TKE values and also increases the accuracy of the final Reynolds stress tensor. And this is constant in both TBCAN and the modified TBNN framework. And again, this is adapted from the KCNN formulation in McConkey et al., which is our reference 6. Just quickly going over the loss function and the realizability penalty, which is also, I want to say, a novelty of this part of the paper, which is that we are combining the loss with the RBIJ, which is the penalty function for the normalized Reynolds stress tensor. So the reason why we penalize values that are non-realizable is because we want to make sure that the Reynolds stresses that are predicted are physically realizable, which means they're positive semi-definite. And alpha is sort of a weight that we selected based on some prior evaluations, and we go with the value of 100. This is because this this just penalizes the architecture like super heavily if we're like outside in the non-realizable zone. So we have tested this over 3 test cases. So we have the flat plate, square duct, and the periodic hills. The flat plate is a good example for anisotropic prediction near the wall. The square duct has secondary flows due to corner vortices, and periodic hills is a good example for flow separation and reattachment. Just briefly going over the setup for the flat plate case. It's the zero pressure gradient turbulent boundary layer from NASA. And the objective is to test TB-CAN's capability in a simple wall-bounded flow. And then the loss function, as I mentioned, we are still using the same realizability penalty and the Forbius norm between the predicted and the DNS values for AIJ. So the input features for the flat plate are 6 scalar invariants. So from the massive list of the scalar invariants we have 6 inputs which are derived from the K omega SST model. So the TB-CAN architecture for this one is just a 1-layer configuration with B splines and a grid size of 8 control points and cubic splines. So our K value is 3. And the TBNN architecture is the 4 layers with 20 neurons per layer. So it's so if we compare the model, just the mean squared error in AIJ, TB-CAN has a 0.22, and then TBNN, the modified TBNN has 0.19. So over here, we're going to compare the learnable parameters. So TB-CAN has around 1,100 learnable parameters, whereas the modified TBNN has 1,600. It does have a fewer learnable parameters, and it does give a similar performance for AIJ. But the number of learnable parameters sort of increase as we go, the difference between them increases as we go down from the flat plate to the square duct and the periodic hills case. So just a brief summary of the hyperparameter tuning that we did with the CAN architecture. So the tune parameters were learning rate, the network width, which are essentially neurons per layer, the spline grid size, and the selection of the scalar invariants. And the methodology that we implemented was having 27 random runs, just so that we have like a warm start for Bayesian optimization, and then 150 Bayesian optimization runs. So the optimal setup did achieve a mean squared error of 0.22 in AIJ. And this is the loss curves for both TB-CAN and the modified TBNN. So visually, you can see that TB-CAN has a stable convergence with fewer parameters. Meanwhile, the modified TBNN does achieve a slightly lower mean square error, but at a slightly higher model complexity. And in every case, all 3 cases, we did implement early stopping just so that we don't overfit the model. And if we look at the results for TB-CAN, you can see the A11, 812, 22, and 33. So they are showing good agreement with the DNS data. And as you can see, the A11, 22, and 33 K omega SST just fails to capture it altogether. But the model in itself is fairly well aligned with the DNS results. Versus when you look at the results from modified TBNN prediction for the anisotropic components, visually they do look better, like a better match. So there is a lower error than TB-CAN, but it does have a slightly more complicated architecture. Just so that I mentioned, there's no injection with the flat plate case, but the injection sort of comes into the square duct and the periodic hills cases. So the square duct case is another benchmark case which is used in turbulence modeling because it has secondary flows. So the DNS data for this one is taken from Pinelli, and the baseline RANS data is taken from McConkey. So the Reynolds number is also based on the half height of the duct, and the kinematic viscosity used is also given. So the input features for this one were 16 scalar invariants. So you'll notice that we went from 6 to 16. And the reason for this is because this was a more complicated test case than the flat plate. So we obviously needed more input data. The data set size is also overall larger than the flat plate. And we sort of split the different data sets for different Reynolds number in 3 batches. So we have the training, the validation, and the test set. So the TB-CAN architecture that we came up with was the 3-layer configuration with 8, 7, and 9 neurons per layer, respectively. And the B-spline grid size of 7 control points were used. Versus with the modified TBNN, we had a 7-layer multi-layer perceptron with 30 ReLU-activated neurons per layer. And I'm just summarizing the learning rate architecture in the model in the table below. So just a brief summary of the hyperparameter tuning for this case. So the tuned parameters were learning rate, network width and depth, the grid size, and the feature set, the 16 invariants that we used. So the method was, again, using the 27 random trials as a warm start, and then 143 Bayesian optimization trials. And we also had a early stopping implemented just so that we don't overfit. So the best configuration achieved a mean squared error of 2.39, the 10 raised to the power -8 in AIJ. And then when I say the error in UI, this is where the injection step comes in. So we'll just get into that after this slide. So just looking at the loss curves, so TB-CAN does show a smoother convergence with minimal overfitting, even though the modified TBNN network had a slightly lower loss. It was a bit noisier. So this is the a priori result, essentially comparing the anisotropy tensor and its components. So visually, I think we can say that DNS and the modified TBNN do match really well, whereas the TB-CAN does have some struggles in the A12 and the 13 component of the tensor. But K-omega SST just does not capture any of the 4 of our main components in our matrix. So the TB-CAN predictions, they do show significantly better agreement with DNS compared to RANS, right, in the diagonal components and the off-diagonal components as well, which are the main components that we have to consider for secondary flow. It is capturing the turbulence-driven stress structures, right? But when we compare the modified TBNN to TB-CAN, there would be some differences when we get into the injection part. So this figure here just sort of demonstrates that TB-CAN is capturing the corner vortices and that behavior, which the baseline K-omega SST model fails to, reproduce. And these are the results where we sort of inject back the U2 and the U3 velocities and try to figure out how well does the modified TBNN and the TB-CAN sort of how well they behave when it compares to comparing DNS values. So TBNN and TB-CAN are quite similar, I would like to say, but and they do, like, magnitude-wise are a bit smaller than what it should be when you compare it to DNS, but they are fairly comparable for both U2, which is in this figure, and then U3, which has, you're still following the same structure, but the magnitude is still varied for both the networks. And so something that we can draw from this this test case in particular is that both TB-CAN and TBNN, they do outperform the baseline SST model. And then it can accurately capture the location and the shape of the secondary flow peaks, but the magnitude-wise, it is still slightly underpredicted by both the models. For the last case, the periodic hills, this is another benchmark case with flow separation, reattachment, and the adverse pressure gradients. So the DNS data is taken for the Reynolds number of 5,600, and we have a periodic boundary condition in the streamwise direction and no slip on top and bottom walls. So for both training and evaluation, we're using the TB-CAN and the modified TBNN models. Again, just going over the input features in the data set. So we have a 17 scalar invariants that we're using as our input features for K-omega SST. The DNS data is taken from Zhao et al., and then the RANS baseline data is taken from McConkey et al. And the TB-CAN architecture is another 3-layer configuration with 888 neurons per layer, and then the grid size that we use for cubic B-spline is 5. And the learning rate is also given in our table, which is 1 times 10 raised to the power negative 4. So comparing it to the modified TBN architecture, we use 7 layers and 30 neurons per layer. And the training strategy for this one, unfortunately, we did not do Bayesian optimization for the TB-CAN architecture hyperparameter tuning, but we did random search only. So similar to the other 2 test cases, the tuned parameters were the same, where we had the network width and depth, the grid size, learning rate, and the invariance that we used. So for this one, it was just a random search that was deployed, and the results are in front of you, which were the MSE for 3.18 times 10 raised to the power negative 12 for AIJ, and 3.71 times negative 10 raised to the power negative 8 for UI. And this is where we see the significant parameter reduction compared to the modified TBNN. So just quickly going over the validation losses. So TB-CAN does converge a bit faster, like it does need lesser number of epochs. And TBNN, it does reach a lower loss, but again, it becomes noisier towards the end due to higher model complexity. And visually, if we look at the anisotropy tensor predictions, we can see that it is very comparable. Like TB-CAN and TBNN do both seem very, very similar to each other, just visually. And then K-omega SST again just fails to capture the diagonal components again of the anisotropy tensor. So for this case, both the TB-CAN and the TBNN are significantly outperforming the baseline SST. The TB-CAN does show improved alignment with the DNS, especially for A12 and 33. So this is where the separation and the reattachment zones occur. And it has much fewer parameters when you compare it to the modified TBNN. So this figure here sort of just looks at the normalized U1 profiles at the different streamwise locations. And again, as you can see, TBNN and TB-CAN are following the DNS very, very closely. It's very hard to even differentiate between the two, especially in this figure. But and you can see the TB-CAN is providing a consistent shape in the separated and the recirculation regions for the periodic hills case. So if we just look at the streamwise and the and the spanwise velocity contours for the periodic hills, the injected TBNN prediction, just visually, you can note that at the separation point, it fails to perform as well as TB-CAN for U2. And then similarly, at the reattachment point, the TB-CAN does have some struggle when you compare it to the DNS data. I think this is better visualized when we move to the, so I'll just move here first, the error plots. So here you can see just the velocity error contours. So we're comparing it to the DNS results. So for both U1 and U2, if one is performing better at separation, the other is sort of performing better at reattachment. So they do show reduced velocity error magnitudes across the domain. And again, K-omega SST does have the largest errors near the separation and the reattachment point, which is something that would happen with RANS solvers. And then it is preserving, so both TB-CAN and the TBNN network are preserving physical smoothness. I think the only difference between the two models that is significant here are the number of parameters. So if I sort of summarize the model performance and the complexity, so you have the flat plate, the square duct, and the periodic hills. You can see that the mean squared errors for both the AIJ and the UI terms are like fairly similar, but the number of parameters is where the significant difference occurs. So the MLP network does have more parameters, so almost 50% more in the square duct case, and then almost 80% more in the periodic hills case. So there is significant parameter reduction when we are using the CAN architecture. It is giving us comparable performance with the TBNN, like nothing too different, I would say, like still fairly comparable. And if we look at the model efficiency, so we are reducing the parameter count because of the spline-based approximators, and the training process was smooth with TB-CAN. There was stable convergence across the flows, and there is potential for symbolic regression where the B-spline mappings can be approximated as algebraic expressions, just for more insight. And if we look at the so if we move toward and talk about some key contributions and novelties. So for this entire study, the hybrid injection strategy is something that's not been really used before. So we use both implicit and explicit injection. And then the other part is that the realizability-based regularization. So in previous studies, there's not been any realizability penalty for the loss functions, just to make sure that the anisotropy tensor that's being predicted is staying within the physical plausible bounds. And just to sort of summarize what we've gone through, we have seen that the TB-CAN is providing a robust realizability-informed alternative to MLP-based turbulence closure. So we validated across the three flows, the flat plate, square duct, and periodic hills. There is significant parameter reduction without sacrificing much accuracy. And the injection process for the a posteriori velocity prediction is fairly stable in terrains. So the future work can include extending this the TB-CAN architecture into more 3D and compressible flows at higher Reynolds number, maybe incorporating uncertainty quantification, something that can be maybe look into it in the future, and then exploring symbolic regression for these stress models in general. And these are the links for the paper. So the paper, so that's the archive link actually. It's been accepted to POF. Should be in the August 2025 issue, I believe. And then those are the GitHub repositories for both TB-CAN and TBNN, which are open repositories. And it's there. It's just so if people want to look at it, suggest some changes, it's always good to know. And yeah, those are the references, and thank you.
Great, thank you so much, Nikhila. That was a really nice presentation. Do we have any questions from the audience?
Yes, I have some questions.
Yeah, please.
So this is Ahmed from Brown. I really enjoyed your presentation and the study. So one question that I have, can you elaborate on when you want to use this framework on URANs as a situation when you have unsteady RANs, how you would take it, and then how you would use it in the solver?
Right. So for the unsteady RANs, like we haven't really used it, right? Again, that's a really good question. So I would assume that you still can get your invariance from your URAN simulation, right? Like where you use probably some sort of two equation models, right? But yeah, I'm not sure like if I go back to the architecture super quick, sorry. Okay, over here. So in our architecture, like I feel like as long as you have something to benchmark it against, for example, some high fidelity data that you have that you can benchmark your URANs against, and as long as you have your input layer consisting of the scalar invariance, I think it should be applicable. Again, I have never tested it on any of the URANs problems, which is something obviously interesting and worth looking into.
Because in that situation, you have advancement in time, right?
Yes, you have the DT
term. A step in the solver, you have like the initial solution, and then you take one step, right? So you don't have those stress and those tensors for the later time. So I think the training should be changed.
Yeah, probably. Again, it's something that I'd probably have to read about a lot into before, looking into it. But again, I would say that, the training architecture and the injection would both probably have to change, because the Rand's momentum equation would also change, having the dt term, which is, well, currently not there because it is steady state injection.
Then one more question. So like for periodic hill, so you trained the coefficient on one test case based on that Reynolds number, and then you injected that into the solver and then ran the simulation for the same Reynolds number, right?
No,
Or
no. So the testing Reynolds number is always different to the training and the validation test set. Sorry, I probably should have made that clear. But yes, so the testing RE values for both the square dot, or all three cases actually, have been different. And for the injection, it's also the same one that we tested it on. So that's the one that we're sort of injecting it back into the back into OpenFOAM to get the flow fields.
Okay, thank you. Great result.
Thank you.
Hi, Nikhila. This is Jen from Brown, and I have two questions. One is for the injection part. Could you please turn to the injection of square cylinder, square.
This one, or like the injection of square dot?
Yeah, and the velocity profile.
U2 or U3?
Yeah, here. Yes.
Okay.
So here the injection is by the hybrid. Hybrid. Just implicit plus the explicit integration, right? So you okay, and in that case, there's a difference between the TBN, TBCAN, and DNS. So means So why there's
sorry, go ahead.
Why there's a large difference between the between the DNS and the TBCAN?
Yes, so that's a good question, because as I said, as I mentioned, like magnitude wise, both of them are, well, let's think of it in a perspective. U2 and U3 are your, the velocities in your y and z direction, right? So regardless, if I go back to the setup case, so this is a purely streamwise flow. So the secondary flows in the corner vortices are like really, really tiny. Like if you look at the magnitude of it, right? Like it's, I think, like super small, maybe like 10 raised to the power -8 or something, to that order. So it's already like super small, and then super hard to even capture. Like k omega SST just does not capture it because it averages it out, right? So I think, which is why we see like the magnitude peaks being different, but the fact that TBNN and TBCAN can still like sort of capture where they're being formed is more of what this shows. But yes, you're right. Like magnitude wise, it is more away from DNS, just because of the accuracy the two equation models have.
And I think, but I noticed the difference between the difference of the AIJ. If maybe it's in the previous slide.
This one?
Yeah, so it is pretty good. So is this result from the coupled system, or you just from the directly output of the TBN?
So this one is direct output. So this comes as an a priori test. So AIJ is coming directly from the first architecture that I showed. So if I just like run back, so the AIJ that you're seeing is the a priori test and not the injection test. The injection one is limited to the U profiles, the U2 and the U3. So this one over here is essentially, if I can bring my mouse here, is this AIJ term that you're getting, and then you're comparing it to the DNS one.
Yes,
that's our that's
I got it. Yeah, but I think we are also interested in the the AIJ term from the coupled system. So as you did with the velocity profile, you can also compare that AIJ against the DNS, right?
So this AIJ that we're getting is pretty much taking that AIJ and inputting it into this structure, if that makes sense. So you're just like bringing the AIJ that you compute and then sort of inputting it in this, wait, where's my mouse? Rand's equation.
Um,
I guess your question is like, what happened to the first term, right? Like, or
oh, so here you just take the G1 term as the new TR here, and
yes.
okay.
So yes, so the G1 is just the new T, well, R, which just sort of goes here.
And the other parts are all in the AIJ orthogonal term.
So yeah, so this one is explicit. So the G2 to G10 would be the explicit part.
Yeah, but I think only the GN are the output of the, say, neural network, but the TIJ, the tensor bases, are coming from the solver, right? If you plug this model into the...
So this, the TIJ parts are just being multiplied into GN. So these like are just like getting multiplied and summed together.
Yeah. So I'm curious, when you plug this model into the open form, so where the GI come from? So
the GN is still from the
initial
first,
training data.
Yeah, the training.
I see.
Yeah.
Okay, so you are somehow read the field of the AIJ orthogonal term.
Sorry, can you say that again? I think it just missed. I missed out the last sentence.
Yes. So the last term, so AIJ orthogonal, tilde. So you just read this term, read this field into the open form as an explicit force. I see. Okay. And another question is about the input feature. You mentioned you have 16 or 17 features.
Yes.
Could you please show what are they?
So these are like scalars. So the first, if I go back to maybe, let's see. Yeah, I don't have the list of the input features on the presentation, unfortunately. But if I go back here, so the Ling paper from 2016, they introduced using, I believe, lambda 1 through lambda 5 as their inputs, right? Which they come up with Sij and Rij, right? That's how they derive those. So Wu et al., that paper uses the gradient for the omega, k, and then pressure as well to come up with another list of scalar invariants. But then McConkey et al., they don't use the pressure, what was the word I was looking for? They don't use the pressure ones. They only use Sij, Rij, and then on top of that, the omega and the k. So they dropped the pressure one because, it's apparently you lose Galilean invariance if you use that or something.
Okay, so you derived all of the 16 scalars from the Sij, Rij, and the gradient of the omega and k,
omega and
pressure.
K. Yes. No, we didn't use the pressure ones. So the pressure ones was used in Wu, but we didn't use that.
Okay, yeah, got it. Thank you. That's nice presentation.
Great, thank you, Tim, for your questions. Do you have any other questions from the audience?
Hi, Nikhila. I have a small question. You talk about the number of parameter reduced in the CAN. What about the time, training time?
Great question. I knew someone was going to ask me that. So when we compare, the only reason why we're not comparing training times is because the hardware used for training the MLP-based modified TBNN and TBCAN were different. So it would be an unfair comparison. But I understand because CANs have the, the B-spline, it is, that's just my personal opinion. I just think it was a bit slower that compared to the MLP. But again, I can make a definite call on that just because they were both trained on like separate hardware devices, because this study was essentially a continuation of a previous study, and the previous study did MLP, and we were like, okay, so CANs is something new. What happens if we sort of try the same thing or the same test cases with CANs instead and change our network based on that?
Okay, yeah, thank you.
It is very expensive. That's why one, for example, was the first to do that study. He found that splines are, I mean, in the group here, we use Chebyshev can.
Yes.
So we abandon splines the first day that we use them. So
no, you're 100% right. They are slower, as you mentioned, and the Chebyshev can is. Do you also have a GitHub repository for that? Because we are actually looking into using Chebyshev as well, just to see if they sort of.
One has, I think.
Okay.
Yeah, I put it. Yeah, I have it. I can put it in the chat.
Oh, thank you. Because that was our next step, because we were like, okay, this is not fast.
Yeah. Actually, even in the original paper, like they say that it can be up to 10 times slower, but if for longer networks, it can be up to 100 times slower. So it's crazy.
Yeah.
Painfully slow.
No. Yes. So I think in the original paper, again, please correct me if I'm wrong. It was the problems themselves were not very complex, and when you go to a complicated problem such as this one, it just becomes very, very slow. Even though I think they updated their GitHub repo with saying that you can turn off the symbolic part. Even after turning it off, it was still slow.
Yes.
That was just my personal experience.
Yeah.
And I believe that is, even though they do produce results. And another problem that I did see just by training this was something that cancer actually, they have a tendency to overfit pretty fast. I don't know if that is something you observed while working on it, but for these cases, especially the more complicated one, overfitting personally was something that I saw in a lot of test runs, which is, it's kind of like overfitting like super fast. But
Yeah.
Can we go back to the, sorry, Juan. Can we go back to the instability, to the
yes, of course.
injection method? So how did you end up using G1 implicitly and then the other one explicitly? Was it, I mean, you...
So the main reason, the first reason for this was when you have just explicit injection, because I think Link's paper also just had explicit injection in their paper. So convergence becomes an issue, like just stability of the solver itself. So in McConkey's paper, they start with using G1 implicit just to get the new T from from rent. So it stabilizes the entire equation, and then you're not.
Can I say something? So if this was, is it hierarchical? It's not hierarchical, right? So when you make one implicit, the other ones, you're not prioritizing the physics. So why can I use G8 to be implicit?
I think the reason why we use G1 is because that comes. So if I go back here, sorry. So you see the coefficient is just like this. It's a simple mathematical formulation, versus I think G8 just becomes very complicated. You just have the. I think that's just if I go back to these bigger ones. Well, the coefficient for this is just very.
I see, because it says Sij. Yeah, it's the standard formulation. It reduces to the standard. Yeah. Got it. And you don't need more terms to be implicit. That you found that this is stable for all three flows. I see.
Yes.
Yeah, that's useful information. Yeah.
Maybe I have just a short question here. Maybe like a philosophical question. If you use tensor basis, if you use, can you still call that a can?
Sorry. So if I use
if you use tensor product, can you still consider it as a can?
I guess the reason why we consider it as can or named it can is just from what architecture we're using. So just previously it's just been MLP, and then we changed the architecture, and then you make some changes to your code. So which is why we just call it can, because the architecture we're using at the end of the day is still the spline based one.
Yeah, but in the end, the can, instead of doing tensor product, you usually add all your features you add them together. And I'm saying that because actually, when you work with the card version, like the Kolmogorov-Arnold representation theorem, only allows you to do sums and just sums,
Yep.
not nothing else. But I think that is fine because even there's this CAN 2.0 by the same authors, but Siming and Nishon, and they do tensor product. But it's just it's fine.
Fair enough. I don't know. I just call it CAN.
Yeah, but I think that it would be more accurate, like MLP with a feature expansion or something like that. But that's it. Yeah. Do you have any other questions from the audience?
Can I ask one more question?
Mm-hmm.
So can we have a situation to train the network on, let's say, channel flow and then test it on a periodic hills, or what kind of a strategy we should choose for training? Have you thought
That
about
would probably not work really well.
Yeah, I understand that, but like in future,
Mhm.
if you want to build something that is like useful and we can use it in solvers, like in general,
Yes.
what would be the best
So
thing for that, you think?
I think I'm gonna answer this question in like two parts, if that's okay. So part one is that just admitting and understanding, like, flow generalization is a very hard thing to do. And just as an example, so we have the flow over the bump, right? And then you have like different bump heights. I feel like it's easier to generalize for flows like that. Like, okay, we do the entire architecture, everything for like one flow type, and then we increase the bump height and maybe we can get a better generalizability over there. Versus when we go from like something, a duct flow, right? Like from a square duct maybe to a rectangular duct, sure. I think generalizability there might also be somewhat possible, but then going from like a duct flow to like predicting periodic hills, I just think it's gonna not work personally.
Yeah,
But then
one example, but what I meant, like, can we like categorize the physics? Like we have separation, we have reattachment, we have other physics, and have a data set that can cover like general physics of turbulence, and then
right.
use that for the data set. That's what I meant.
I feel like for similar type of flows, maybe that is possible. It just depends like how general we're talking, right? Like a flat plate case, if we do that and then we expect it to work on periodic hills, that's probably not going to work. But yes, I understand what you mean. Like example wise, it still has to be somewhat similar geometrically to sort of quantify generalizability. I don't think like generalizability can work from like comparing, I want to say like comparing apples to apples and not apples to oranges, because that would probably not work well. Or maybe someone can do it, but so far I just personally don't think that that would happen.
Yeah. Thank you.
Great. Do we have any other questions from the audience? It looks like we do not. Thank you so much, Nikhila. This was a really nice presentation. And thank you everyone for your time today. And with this, I think we can close today's seminar.
All right. Thank you so much.